Okay, today we're going to discuss same problem really, Toyota Corolla predicting the price, but we're going to take it one step further, okay? What we did so far is we tried to model the price of Toyota Corolla used cars based on only one independent variable predictor, right? That would be mileage. We said mileage is probably the strongest predictor out there, okay? Which probably is true. So go ahead and open up the file. So open up Jump, and there should be a file Toyota Corolla, the one that we used in the last couple of classes, okay? And just a quick reminder, here's what we did so far. We said, okay, let's try to build a linear regression, right? So we said fit the model, and that was originally simple linear regression. Why? Because there was only one predictor, right? Only one independent variable. That's what makes it simple. So we said price is my target, mileage is my independent variable, predictor or effect, like Jump calls it. And when I click run, here is the result of analysis for me. So we have estimate of the parameters, and that means we have two of them, right? We have intercept and the slope. Intercept is just a fixed number, and slope that corresponds to the only one variable that I've selected, my independent predictor, okay? And after that we said, well, kind of assessment of how closely my model fits the data is included in the summary of fit, and that's R squared, right? So right there, 0.355. So how do I interpret that? I basically say that the variability in cars' mileages explains about 36% of the variability in car prices, right? So single-handedly, the variable mileage is responsible for about 36% of the variability in terms of the car prices, okay? And we said that it's not the greatest of the models, because 35% is not huge, right, by any stretch of imagination. So therefore, it's an okay model. I'd say it's moderately accurate, not terribly great model, but still, it's not bad as well. And then we said, well, look, it looks like in the residuals plot we have some sort of the weird curvature going on, right? It looks like first residuals were positive, and then they became mostly negative, and then they became mostly positive again. So that calls for an adjustment, right? We said, how about we're going to fix that curvature by adding a quadratic term, right? So I'm going to rerun the model and click the recall button so that it says that the price is my predictor, target, and the mileage is my predictor. But now I'm going to introduce into the model mileage squared. So I'm starting to make up things that were not part of my original model, right? In data analytics field, it's called feature engineering. It's a very powerful mechanism, okay? So this is where kind of it stops being science as much as it becomes an art, okay? What's feature engineering? Feature engineering is, these are all of my features, right? These are all of my model variables that I have in my data set. Age, mileage, horsepower, how many doors, color, all these things, right? That's what I'm given. I have to work with this, right? Oh, look at that. My daughter is online. Okay. What I can do is, in order to build a better model, I can somehow combine the variables that are given to me to create a new combination variable, okay? Engineered feature. So it's not part of the original data set, but I can compute that from the things that I'm given, okay? And if I'm lucky, and I create such a beautiful combination, such a powerful combination, I can tremendously improve the predictive accuracy of my model, okay? That, of course, there are no predefined guidelines how to do that. There are just general recommendations, things that you can try and hope that it will result in a good model accuracy, okay? But to a large degree, it's a matter of looking at the data, visualizing different variables, and trying to see what happens and what could be a good combination, okay? So in my case, what I looked at was scatter plot, right, of residuals, and I said, well, it looks like it has a curvature, so it could be that if I do something with the mileage, like square it, for example, it could be a linear, it could be a good new feature. So I'm kind of engineering things from what I'm given, right? Very powerful technique, again, if you like, and if you get a really good combination that has something to do, a lot to do with your target, you can build a very powerful model, okay? But, like I said, it's more of an art rather than science, okay? So what I'm going to do, what we did, I believe, in the previous class is said mileage and mileage. Well, let's make a cross. So that creates mileage squared, right? The thing that was not part of my original data set, I created that, okay, out of things that I'm given. And if I run the model again, my R squared goes higher, I believe, right? My R squared from 36% goes to 45%. So there is a substantial gain, right? My model became more accurate. Now, mileage and mileage squared explain about 45% of the price variabilities, right? And my residual plot actually is much more well behaved, right? So that's just an example how model can be improved by using the feature engineering. But what I wanted to do today is do something a little bit different, okay? So far, what I used in my model was only mileage, and that's it, nothing else, right? Well, I have a bunch of other things, right? So I can use other variables, throw them into the model, and hopefully the model will become better and better and better. The more things I add, the better it becomes, right? Why? Because I'm capturing more aspects of the reality. So when I'm using mileage only, I'm saying mileage is the only thing that's important. No, it's not. There are other things, right? Number of owners, horsepower of the car probably has a lot to do with the price, right? Horsepower, it's proportional to the number of cylinders, to the volume of the engine, right? And like BMW, for example, right? Muscle car. It has big engine, so therefore it has high horsepower and it's typically expensive, right? So other things can influence the price of the car, not the mileage, but something else. So here is what I'm planning to do, okay? I'm planning to construct something that is called multiple regression, okay? Multiple regression. And again, it's multiple linear regression, okay? So in the multiple regression, here's how the model looks like. So I'm going to write it in general terms, okay? Y, my target variable, is equal to an intercept plus first slope times my first variable plus the second slope times my second variable plus third slope times the third variable plus how many variables can I add to the model? As many as I want, right? As long as I have the data, I can throw all of them for all I care into the model and hope that that will create a great, powerful, accurate model that closely fits my data, right? And finally, so I'm going to put ... Finally, I understand that probably no matter how many variables I'm going to throw into the model, it will not 100%, it's not going to be 100% accurate, right? So therefore, there's going to be always a noise, random noise. So I'm going to add epsilon, which essentially will tell me, hey, you know, this is a random variable, okay? Things happen just randomly. Because one dealer, you know, just says, okay, what the hell, let's increase the price by $400, it's negotiable, right? But let's just bump up the price, okay, sticker. So random decision. All right, so you can see why it's called multiple, right? Because as opposed to simple, where I have only one predictor, x1, right? Now I have many predictors, many regressors. These variables, independent variables, are also called regressors when we're dealing with regression. So in my case, I'm going to build up a model which is bigger and bigger and bigger. So let's start with adding, for example, age of the car, okay? So I'm going to specifically try to do this. Price equals to beta 0 plus beta 1. Still I'm going to keep mileage, right? Because mileage seems to be a good variable. Mileage plus beta 2 times age of the car, okay? Well, let's kind of start slowly, all right? All right, so let's go back. And here's my age and mileage. So these are the two. Now note that I'm dealing right now with only numerical variables, right? When I'm dealing with regression, my target is always numerical. It's always continuous, okay? And so far, I dealt with mileage. Now I'm about to include the age, okay? So my predictors are also continuous. So actually, you know what? Before we go further, what I wanted to do is update our document. Remember, I gave you a handout some time ago. It's kind of a map of all the tools, right? So far we covered 2 tools, right? We covered classification tree, and you use classification tree when your target is categorical, right? When you're predicting whether or not the student will return or drop out of the university, right? Whether or not the customer of the bank will default on the loan or not default, right? Things like that. Yes, no, 0, 1, true, false. Okay, so classification tree. And then you can predict the numerical variable using the tree structure. In this case, you're dealing with regression tree, right? Okay, so so far we were predicting the car price in that specific example, right? Using the mileage. So our target, the car price, is what type of the variable? Continuous, right? And the mileage is also continuous, right? So therefore, my target is continuous, and my predictors, right? Independent variables are continuous. So regression tree was our first model that we used, and you can use alternatively linear regression. Okay, let's call it multiple linear regression. Multiple because we're about to explore that. Nobody really stops at the simple linear regression, right? The more variables you throw, the better you predict the reality, okay? Closer you are modeling the real life situation. So multiple linear regression. So continuous predictors, continuous target. Okay, so let's go back to our thingy. Whoopsie, what did I do? Let's go back to Toyota Corolla. So I'm going to expand my model, and it's actually really simple. So what I'm going to do is, again, price is my target, and age and mileage together I'm going to add to the model effects. All right? Both continuous random variables, and that's it pretty much. So now I'm going to have to click the run button, and here is my model. Okay? All right. So thing number 1 is let's take a look at the equation. Okay? What is the predictor equation? So I need to look at the estimates of my slope and the intercepts, right? No, one intercept and multiple slopes, other way around. So intercept is 21,340.7. All right. So let me write that down. So here's my equation. 21. Oh God, I forgot it already. 21,348.7. 348.7. Then first one is the mileage, right? And the mileage has the slope of negative 0.01795, negative 0.01795 times the mileage. And age is probably also negative, right? The older car becomes, the lower the price, right? That's kind of common sense, right? So, is it? Yeah, it looks like it is, right? Our regression tells me that my age of the car has a negative slope, which is aligned with my common sense, right? The older car loses the value, right? Everything else being equal. So, minus, oh God, what was that? 173.9 minus 173.9 times the age of the car. Okay? All right. So, how do I interpret my my coefficients of the model? Well, pretty much same as before, right? Remember, when we did the interpretation of the coefficients of the model, what did we say? If I increase the age of the car by 1, from age I go to age plus 1, whatever was the age, right? So right now I have, for example, the car that's 5 years old, right? So if I stop driving it, if I keep mileage the same, right? So put it in the garage for 1 year. Mileage stays the same, right? But 1 year later, I'm going to take it out of the garage and start driving it. How much this car is going to worth? Well, since age went from age to age plus 1, right? That means that from my old price, I have to subtract that much, right? So the interpretation of the slope is, if I hold all other variables the same, unchanged, mileage is the same, not changed, right? But this one is increased by 1, age goes up by 1, the car loses how much? $173, almost $74 in value, right? So age goes up by 1, other variables being held constant, that's how much value the car loses, right? Similar interpretation is for mileage slope, right? What was the interpretation? If I keep the age the same, but put mileage plus 1, so I drive car 1 extra mile, right? It loses the value. How much? Well, that much. Because of this plus 1, I have to subtract 0.001795, right? And that would be of the euro, right? Because all prices are in euros, right? So every extra mile that I put on the car while driving it reduces the value price of the car by what? Almost 20, no, by what, 0.01 cent. It's like 2 euro cents, right? 1.7 euro cents, right? Make sense? And remember, how did we describe this one? How did we interpret this one? We said if mileage equals to 0, and age equals to 0, which corresponds to what? Car which has no miles and the age is 0. A brand new car, right? A brand new car value is 21,348.7 euros, right? But then here we have to be careful, right? We have to make sure that our regression includes the points, the scatter plot, the data set, right? Includes the points that actually have mileage is close to 0 and age is close to 0, right? Because otherwise I may be extending my model into the area where this model is actually doesn't hold, okay? It's not relevant, right? We discussed that in previous classes. Okay, so that's the main output of my model, right? The equation. All right, now let's take a look at the accuracy. Remember how much was my R squared when I calculated, when I built the model using only mileage alone? It was 36%, right? 0.36. So is that better? Oh gosh golly, yes, it's better, right? So it was 36%. Now I'm dealing with R squared of 0.77, right? So that's quite a jump, right, in accuracy. Now I'm dealing with PDG model, right? Pretty darn good model, okay? So these two variables, the variability in car mileages and car ages taken together, explain about 77% of variability from car to car in terms of their prices, right? So about 27% of the variability in car prices is not explained by these two variables, right? Okay, so this is a pretty good model. Now, here is what we need to test, okay? This is all good and dandy, but unfortunately, I have to do some damage control, some testing, okay? So here is what is standardly tested, okay? Let's go back to the drawing board. Let me start a new page. First of all, I'm going to have to test the model overall for the validity. So there are two tests, okay? In the previous, when we were dealing with simple linear regression, we did only one test for the slope, right? The slope equal to 0 and the model is valid. Or if the slope is not 0, no, other way around. If the slope is 0, model is invalid, right? And if the slope is not 0 statistically, that means that the model has something to do with the reality. That's the only test that we did. Here, when we're dealing with multiple regression, we're going to have to do two types of tests, okay? So, type number 1, overall validity of the model, okay? Overall, keyword overall here, model validity, okay? Here is what I'm testing. My null hypothesis is that all the slopes together simultaneously can be set to 0, and the model will be just as good as the one that I have right now. In other words, right now I have two variables, right? I have age or mileage. What's the mileage first one, right? So slope for the mileage is equal to the slope for the age of the car, and they're both equal to 0. If both slopes are equal to 0, what does that mean? That means that, in my model, if that slope is equal to 0 and that slope is equal to 0, that means that no matter what ages and mileages I get, the price is not going to change, right? So therefore, are these important variables, mileage and age? No, not really, right? They don't affect anything. So therefore, my model is non-existent really, okay? So therefore, if I find in favor of the null hypothesis this one, it actually means that the model is not statistically significant, okay? Model is not significant overall, okay? So it's as if I don't have a model. This model is equivalent to no model at all, just as good as nothing really, okay? Alternatively, if at least one of my slopes is different from 0, that means that at least one of the variables has something to do with price of the car. Okay? So therefore my alternative is going to be that at least one slope, I'm going to call it beta with a subscript I. I can have more than one, right? More than 2, more than 3. Okay, at least one slope is not equal to 0, which means that the model is valid overall. Overall, again, is the keyword here, overall, okay? All right, and like we discussed in the previous class, if we have a hypothesis test, what do we need? That comes with testing, starts with P, ends with value, right? So p-value. In order to see if the p-value, which one of my hypotheses is the case, I need to take a look at the p-value, right? Let's take a look at the p-value. Where do I find it? Right here, okay? Lack of fit, this section, all right? There is F ratio, that's the statistic that they compute. Behind the scenes, I'm not going to go into details. It's opening completely different can of worms, and we don't want to go there, okay? So, probability greater than that F value is your p-value, okay? So, 0.0028. I'm going to go back. P-value is 0.0028. And in order to make a determination, I need to compare my p-value against alpha, right? What's the standard value of alpha that we're using? 0.05, right? Now let's do that. Because why shouldn't we, right? Unless specified otherwise, let's use 5%. Clearly, the p-value is less than alpha. What happens if my p-value is less than alpha? What do I do? I accept the alternative, right? I reject the null in favor of alternative, right? So therefore, I reject the null in favor of alternative. And my alternative says that at least one slope got to be not 0, right? That means that at least one of my independent variables, predictors, it is actually statistically linked and connected with the price of the car. So my model, considered overall, is valid, good and dandy. Okay, but that's the first type of testing that I do. Second type of testing is not all the variables may be important. Okay, not all the variables may contribute to my model. How do I tell? Well, I test each variable individually, okay? So testing, number 2, right? Testing each variable significance, okay? So specifically, here is what happens, okay? My first hypothesis that I'm testing, I'm going to test mileage, okay? And it's the same as we did for the simple linear regression. So my null is going to be that the slope for the mileage can be set to 0, and the alternative obviously is what mileage is not, opposite, right? Slope for the mileage cannot be set to 0. What happens if I find in favor of the null hypothesis? What does that tell me about the mileage variable? Is it significant or not? Not significant, right? If I set the slope to 0, whatever mileage I multiplied doesn't really have an effect at all, right? So therefore, null, if I find in favor of null, mileage is not a significant variable. Significant predictor. Okay? And obviously, alternative is opposite, so I'm not going to write that out, right? And my second hypothesis, I'm going to do the same thing, exactly same thing, but for the age variable, right? So my null is going to be that the slope for the age variable can be set to 0, making it a useless variable for me, right? And the alternative is that the slope for the age variable cannot be set to 0, therefore it's got to stay, and age impacts the mileage, right, significantly. Okay? Alrighty, so we have two hypotheses, we need two p-values, right, where to find them. Let's go back to the output. Let's scroll down to the place where we found the parameter estimates, right? So, look at that. Age, here is my slope, and here is the probability greater than t, right? And mileage, same thing. Here is my slope, probability greater than t. So these two probabilities are p-values that I'm looking for, okay? So for the mileages, small value. In fact, if you hover the mouse over this thing, right? Let's see. Kind of worked over here, but then it stopped. What the heck? It will actually tell you precisely the value, right? So, yeah, it doesn't want to do that anymore. So, very small value, right? Both of them are less than 0.0001, okay? So, here p-value, let's write down 0.0001. It's less than any alpha that I can possibly use, right? It's less than 1%, it's less than 5%, it's less than 10%. So, therefore, what do I do with null and alternative? Accept the alternative, right? So I reject the null in favor of alternative, and my alternative says that the mileage is significant or not. What does the alternative say? Not significant? No. It is significant, right? Slope has to stay in the equation, right? Same thing with my age, right? P-value, very small. Let's say it's 0.0001, less than any alpha that I can possibly use, right? Realistic alpha. So therefore, once again, I reject the null in favor of alternative, and it says that the age is also an important variable. Both of them do contribute significantly to my model. Okay? Make sense? Any questions? Concerns, complaints, sarcastic comments? Well, let's take it one step further, right? So, oh, by the way, residual plot. What do you think? Is it good or is it bad? Here's the residual plot. Do you see any issues like heteroskedasticity or any curves, patterns? Well, there may be, like if you have certain degree of imagination, you can probably think that, hey, here is the curvature, right? Slight curvature going on. Okay? So it may or may not indicate the problem. It's hard to tell right now. Well, let's add more stuff, right? And hopefully the model will become even better. Okay? So I'm going to go into the same thing, fit the model, right? Recall. So price is my target, and age and mileage are predictors, and now I'm going to throw in the horsepower. Okay? So in other words, I'm expanding my equation, right? I'm throwing in more and more and more variables, and hopefully I'm building better and better model that fits the data, right? So I click the run button. Well, let's look at the equation first, right? Equation, by the way, every time when you rerun this thing, right, it adjusts all the parameters. So your intercepts and slopes change numerically. That makes sense, right? You try a different model, your numbers will change. So my intercept now is 1638, right? 16,380 euros. The age has practically the same slope, right? What was that? 174 something. So age practically didn't change, right? Still one extra year put on the car, with mileage being the same and the horsepower being the same. That reduces the value by 174 bucks, right? Mileage also practically didn't change, right? Well, slightly. It was, I believe, 0.017, and now it became 0.0109. So every extra mile that you put on the car reduces the value of the car by what? By 1.09 euro cents, right? And horsepower, how do we interpret the horsepower? Horsepower, by the way, has the positive sign, right? It has the positive impact. So that means that if you keep the car the same age and same mileage on the car, but somehow you increase the horsepower. I don't quite know how to do it physically. What, you replace an engine or something, right? How do you increase the horsepower of the car without replacing an engine? Probably no way, right? But say we can, all right? Say we can add a little bit to the engine, right? Or to the, I don't know, use some fuel efficient injector or whatever the heck it can be, right? So horsepower goes up by 1 without changing age of the car and mileage of the car. It basically tells you that with every extra horsepower, right, every unit of horsepower, the value goes up or down. It goes up, right, by how much? 44.6 euros, right? Okay, cool. Let's take a look at the model accuracy. The previous one was how much was R squared? R squared was like 77, right? Percent, 0.77. So this one, I hope it will go up, right? Well, where's my R squared? It's summary of feet, right? 0.80. So the model accuracy did increase, right? It went up by about 3%. Is that a huge jump? Model went from 77% fit to the data to 80%. It's not a big jump, right? And here is the word of caution, okay? Every time when you add a variable, it's not a word of caution, this is the reality, okay? So, here is the thing. Every time when people build a model using the multiple regression, statisticians are always inclined to include as many variables as possible. The truth is, if you add another variable to the model, the R squared will go up. It cannot go down, okay? The model will not get worse. It will maybe stay the same, but likely R squared will go up. So therefore, if I'm a statistician building a model, what's my inclination? In order to build a kick-ass model, I'm going to throw everything that I have at it, right? I'm going to add more and more things into the model. And R squared is bound to go up. There is no way, okay? It can either stay the same or improve. So therefore, I may be inclined to throw more and more and more variables. But what's the danger of this approach? Overfitting, right? I can be throwing garbage variables into the model, right? Because there can be some accidental correlation. For example, let me give you kind of an extreme example, okay? An extreme example like this. Let's say I'm going to try and predict the price of the Microsoft stock on the stock market in order for me to buy, sell stocks, right? And I can use the temperature daily, so I'm predicting daily price of the Microsoft stock on the stock exchange, and I'm going to use temperature in Newport News to predict the Microsoft stock. Do these two things have anything to do with each other? How much the temperature in the Newport News versus how much the Microsoft stock is worth? Nothing. Nothing at all, right? But if I add that into the variable, this variable into the model, the temperature in Newport News, the R squared will go up, okay? It will go up. Maybe by a teeny tiny insignificant amount, but it will improve, okay? Clearly, the variable that has nothing to do with the model improves the accuracy. So therefore, there is a danger of overfitting, right? You throw garbage variables, you throw the noise into the model, and the model becomes better, okay? So how do we take care of the garbage variables? Okay, not entering the model. Couple of things. Thing number one. Thing number one is if you add to the model a variable which is essentially not contributing much to the model, that purely accidental correlation, okay, not really relevant. One thing that you will notice is your R squared will go up, but by a very small amount, okay? Remember what happened when we added the age variable. R squared jumped a lot, right? Jumped from 36 to 77. Wow, that's a lot, okay? But if you add the variable which is not significant, you will see teeny tiny increase of R squared. That would be your first sign that you are not actually adding value to the model. And this is probably an accidental variable which shouldn't be there, okay? So that's number one. Number two is, remember with the testing that we just did, testing of each variable individually, that's another way how to filter out insignificant variables that are not contributing, okay? So let's do that in our case, right? So what are we looking for? Well, first of all, let's go back to my, where was my overall, right? We need to test my new model with overall validity, but now I have expanded my model a little bit, right? So here, let me erase that stuff. My alternative stays the same, right? At least one variable, blah, 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 is non-zero, right? But my null becomes a little bit different. My null says mileage equals to the h, and now I have the third one, right? What was that? Horsepower, right? HP, let me abbreviate. Horsepower, all of them are equal to 0. Okay? So that's the hypothesis that I'm testing right now for the overall validity of the model. Okay? Where do I find the p-value? Remember that? Lack of fit? Here. Right? My p-value for that one is 0.0014. Cool. So p-value 0.0014. What do I do with this p-value? Keep null or reject the null? Reject the null, right? Very small p-value, less than even 1%. So reject the null in favor of alternative. So therefore my model overall is good, right? That these three variables, at least one of them has something to do with the price of the car. That's cool. Now, I'm going to do the same exact testing. Where is my... Yeah, test each variable significance, right? So before I tested mileage, age, and now I have the third one, right? I'm going to write out the same hypothesis, that the slope for the horsepower equals to 0, making it not a significant variable, right? And the alternative would be the slope for the horsepower is not equal to 0, making it a significant variable, okay? So let's take a look at the p-values. We have three hypotheses to test. We need three p-values, right? So let's go back. Where to find them? Again, I'm going to browse down to the bottom where the parameter estimates are. Here's my p-value for the age. Here's my p-value for the mileage. Here's the p-value for the horsepower. All of them are small, right? All of them are less than 1%. That means that all of my three hypotheses, what do I do with null? Reject it in favor of alternative, right? So that means that my mileage is a significant variable. My age is a significant variable. And here my p-value is also small, right? It was less than 0.0001, but I'm going to just write it out like that, okay? Less than any reasonable value of alpha that we can use. And once again, I reject the null in favor of alternative, which turns out that my horsepower is also a significant variable, right? So this teeny tiny increment of r squared in the amount of 0.03, right? It went from 77% to 80% when I threw into the mix the horsepower, right? It was actually big enough increase for the model to say, yep, that variable is useful, okay? In spite of the fact that its contribution to the model is not that great, but it is a useful variable, okay? Make sense? Any questions, y'all? Anything at all? Because we have one more important thing to discuss, okay? Anything unclear, hazy, shady, weird, plain wacky? All right. One more thing that we have to be really careful about is called multicollinearity, okay? Multicollinearity is a problem that we have to avoid at all costs. Now let's discuss multicollinearity. Multicollinearity. Remember the term multicollinearity from statistics? 231? Or not exactly? Who remembers multicollinearity from statistics? Okay, here goes. Multicollinearity. Remember how we call the variable y, price in my case. We call it target or also dependent variable, right? Remember how we call variables x. In my case, it's age, horsepower, and the mileage. We call them predictors or independent variables, right? For the variables to be truly independent, they also have to be independent from each other. Okay, sometimes it's not the case. Okay? Remember we discussed the coefficient of correlation. And we said coefficient of correlation is the number between what and what? Remind me.
0, 1.
-1 and +1, right? -1 and +1. And after that we kind of discussed informal classification, right? We said that if your coefficient of correlation is close to 0, between -0.3 and +0.3, how do we call that correlation? Strong, moderate, or weak? Weak, right? Weakly correlated variables, right? And then we said if the coefficient of correlation is between 0.3 and 0.7, we call it medium. And if it's close to 1 or -1, if it's between 0.7 and 1, we call it strong, right? Strong correlation. If any of my x variables are strongly correlated with each other, that's bad. That means that if one of the x's increases or decreases, it strongly affects another one, right? That can happen, right? for example, let's say age and mileage can be strongly correlated. Would you agree? If the car gets older, what happens to the mileage? Gets high, right? So therefore, these two variables go together, right? There can be a strong correlation between them. And that's bad, right? If I include both of these variables in the model, it can do weirdest things to my model. In fact, next week we're going to take a look at the examples of precisely that happening to the model, which creates weirdest freaking results. Okay? So therefore, any variables that I use as independent should be truly independent from each other. And independence I'm going to judge based on the coefficient of correlation. So here is the rule of thumb. If any two of the independent variables are highly correlated with each other, I'm going to say that these variables are not independent. And therefore, they should not be used in the model simultaneously together, because they essentially tell you the same story, right? Age goes up, mileage goes up. I'm including both of them, but if they're essentially kind of walking together, right, hand in hand with one another, it's like a double dipping, right? Essentially, I'm including same variable twice almost, right? So how do I look out for multicollinearity? Like, let me summarize. Is it a bad thing, or is it a good thing? High correlation between the independent variables. It's a bad thing, right? We should avoid that, okay? So ideally, there should be no multicollinearity. No two independent variables should be strongly correlated with each other, okay? It should be weak or moderate correlation, but not a strong correlation, okay? How do we test for that? Well, the test is not rigorous, not p-value, but rather informal, okay? So here goes. I need to see about my three independent variables, right? Mileage, age, and horsepower. So here's what I do. I go to the Analyze menu, and then after that, I go to the multivariate methods. Never used it before. And the first option right there says multivariate. Do you see that? Click. Okay. So what it will do, it will create for me the correlation matrix. So here, I'm going to take age and hold control down, mileage, and also horsepower. My three independent variables, right? That's what I'm looking for. I'm not including mileage, okay? They should be strongly correlated with mileage. That's what I want. But between themselves, they should be not correlated strongly at all, right? So I'm picking only my independent variables, predictors. And I put them right there. When I click OK, look what happens. It creates for me the correlation matrix, right? And it also creates for me scatter plots. So let's take a look at the scatter plots, right? Well, at the correlation matrix. First of all, what do you notice? Numbers on the diagonal, what are they? Here. Age with age, how correlated? Perfectly, right? Mileage with mileage, 1.0, perfectly correlated. Horsepower with horsepower, perfectly correlated, right? The variable is always perfectly correlated with itself, right? If you imagine x versus y, your x is mileage and your y is mileage, all the numbers will be aligned at 45-degree angle, right? So we're not going to even look at these things, right? We're not interested that variable correlated with itself. It's always perfectly +1, right? We're going to be interested between mileage and age, right? Mileage and horsepower, and age and horsepower. They're mutual correlation, right? And what are we looking out for? What's the magical number that is going to cut off strong correlation versus not so strong correlation? 0.7 or minus 0.7, right? We should be looking out for strong positive correlation or strong negative, right? So anything that's higher than 0.7 is a strong correlation. Anything lower than minus 0.7 is a strong correlation, right? If I see any of these numbers off diagonal, Houston, I have a problem, right? Agree? So let's take a look. What was our suspicion? Age and mileage are strongly correlated, right? 0.55. It's actually pretty good correlation, right? But is it strong? No, right? It doesn't quite get into this red area of 0.7, right? So I'm going to say it's moderately correlated as I expect, right? Mileage goes up, age goes up. It only makes sense, but it's not quite as strong. So therefore, I don't have a problem there. Okay, age and horsepower, is that a strong correlation? Minus 0.17. Nope, weak, right? How about mileage and the power? Nope. It's kind of moderate, right, on the borderline between weak and moderate, right, but neither of them is strong, right? So do I have a multicollinearity? Thank God, no, right? So this problem, this specific model is problem-free, right? All the variables are good. I didn't see any patterns in the residual plot, and it has no multicollinearity, right? So that's a good model. And it has very decent accuracy, right? 80% R squared. Okay? All right. So ladies and gentlemen, with that in mind, I believe we reached the time limit on this class. So we're going to continue on Friday.